एक्सेस स्लाइड्स देख लो डायरेक्ट, है ना?
आज स्लाइड्स नहीं है ना कुछ भी, वो
स्लाइड्स नहीं मतलब
आज नहीं, हमारे स्लाइड्स नहीं है ना,
हमारा कुछ नहीं, आज क्या स्लाइड दिखाना है?
वही ठीक है।
हाँ यहाँ पे लिखता हूँ मैडम को भी रिमाइंडर देना नहीं ना बाबा।
नहीं मैं कॉल कर दूं क्या अब?
मैं अभी ना करो, रुको पहले ज्वाइन होने
हाँ
तो कर लो।
हाँ ज्वाइन आने दो, फिर मैं कॉल करती चाहिए तो।
मैडम आगे चली जाएगी, बोलेगी नाउ नोबडी इज
हाँ वो बड़ी यस
बोलेगी नोबडी इज देयर, आई एम गोइंग फ्रॉम मीटिंग, क्या करेंगे हम लोग?
नहीं एक्चुअली हमारे मीटिंग में ऐसा करती है मैडम, लेकिन मुझे नहीं लगा था कि प्रोफेशनल एफडीए में ऐसा करेगी मैडम।
आज 3 घंटे का सेशन है, 5-10 मिनट तो रुकना था मुझे।
नहीं सर, शी इज वेरी क्या बोलते हैं आप,
हाँ
बहुत ज्यादा
टाइमिंग
पंक्चुअल है वो टाइमिंग के हिसाब से। हम तो 5 मिनट पहले ज्वाइन करते हैं मीटिंग, फिर हमको डांट खानी पड़ती है। तो मुझे तो अभी तक कभी डांट नहीं खानी पड़ी, लेकिन बहुत लोगों को डांट खानी पड़ती है कि व्हाट इज द टाइम फॉर मीटिंग।
बराबर है। आ गए अश्विनी मैडम, आ गया डॉक्टर अश्विनी गजाबशी मैडम, कशा आहात?
बस छान आहे सर.
अश्विनी आपली
तुम्ही
भेट
सांगा
होत
कशी
नाही
आहे?
आजकाल. अश्विनी मॅडम भेट होत नाही आपली
काय
आता. भेट होत नाही म्हटलं आता, तुमचं डिफेन्स झालं.
जातो ना लॅब मध्ये, त्यामुळे भेट. मी एक तर अर्ली जाते ना, तर लेट
मी येत
इन
नाही आता
त्यामुळे
नाही, मी येत नाही IIT-ला सध्या.
अच्छा असं का? मग काय वर्क?
हो मॅडम, मग कॉलेजच काम भरपूर आहे आम्हाला, संपतच नाही कॉलेजचं काम.
आता त्याचा बदला घेणार आहेत अश्विनी मॅडम. आता जेव्हा कॉलेज चालू होईल ना, तेव्हा वर्क फ्रॉम होम आहे, वर्क फ्रॉम कॉलेज. घरातलं काम कॉलेजला नेऊन भेटायला पाहिजे. म्हणा तुम्ही घरचं काम कसं कॉलेजचं काम कसं घरात करायला सांगितलं, आता आम्ही घरचं काम कसं भेंड्या कापतो.
काय सर? नाही ऐक
म्हटलं कॉलेजला गरज आहे, तर कॉलेज म्हणते ना की वर्क फ्रॉम होम. तर म्हटलं कॉलेज जेव्हा सुरू होईल तेव्हा आपलं घराचं काम पण तिथे न्यायचं, तिथे जाऊन भेंड्या कापायच्या, म्हटलं भाजी बनवायची.
कॉलेज में कुछ भी नहीं है, क्या बनाएंगे वहां पे?
मैडम अभी मैडम को कॉल कर सकते हैं?
ठीक है, आप बाकी कितने पार्टिसिपेंट?
हाँ हाँ अभी ज्वाइन हो गए सब लोग, आगे मैडम आ गए.
हाँ मैडम इज गुड इवनिंग मैम.
Yeah, good evening. Can you hear me?
Yes, I can hear you.
Okay.
Ma'am, sharing rights are
good.
given to you.
Sorry?
Sharing rights are given to you.
Okay, sure. Okay, so what I have done is, because you talked about the lectures, and Professor Rathod mentioned to talk about eventually, like, more in the mode of teaching. So what I'm doing is I'm using some of the lecture slides that I have, and not in a kind of, starting from A to Z. What I will do, I will just focus on some basic points,
okay, ma'am,
and then let's see how it goes. Yeah.
Okay, ma'am, no problem.
So, okay, fine. So I'll share my screen. Just a minute.
So I want to welcome Professor Maryum. Yesterday, after giving a wonderful talk on products of IIT Bombay, you have accepted our request for giving one session of topic of switch capacitor. So I really want to thank you, ma'am, for coming.
Yeah, most welcome. My pleasure to be with all of you, and I'm open to any question as we move ahead. So therefore, it can be an interactive session.
Yes, ma'am.
Yes, ma'am. Thank you, ma'am. Welcome.
Yeah, most welcome. Okay, so I think you should
Yeah.
be able to see my slides.
Yes, ma'am. I can see the slides.
Okay, so let me start. Fortunately, my lectures were in module mode, in the sense that I divided them into different modules. Each module is a short part because it was recorded by CDIP last semester. And therefore it's module wise. So therefore we can start from, say, a module. So it's very convenient. And that is exactly the way it makes it convenient also for occasions like today. Okay, so one of the main principles, by the way, I have also written the textbook that I was using, or I was suggesting students to follow, because that will help them to get more practice and get more materials on the subject, and would be able also to solve some problems, end of chapter problems, to get a hands-on on the analysis of switch capacitor circuits. So switch capacitor circuits find the advantage in bringing the the condition when we are not really relying on elements like O and C, where they can change on the chip in a fabrication process completely independently. And because of this, if you rely on RC, like RC is one of the main parameters which is used for defining the behavior of a filter. Even if we talk about active filters, still you're talking about, say, GM and C, right? So therefore it's very difficult to really to control everything. We have to have tunable circuits. The second point is that in many applications, we actually move to digital domain, and therefore we sample the signal, we give it to ADC, and then we move to digital domain. So if we have that flexibility, so why not to actually use those samples and move to discrete time, something between digital and analog, which is continuous time. So in analog domain, we have continuity in time, we have continuity in values. In digital domain, we have discrete time and discrete values. In discrete time analog value, we have a domain which is in between the two other domains, where we digitize eventually time and make the time to be quantized. But values, still value of the signal still could be any value. So it's not quantized in voltage or current domain or charge domain. So that's why it gives eventually a notion of discrete time processing, which provides us an opportunity to reduce the sensitivity to process variations. And because anyway sampling is available in the system, so we are using that feature. So that is the main motivation behind moving from analog domain to discrete. Okay, so let's talk about this way. Moving from continuous time domain to discrete time domain. It doesn't have anything to do with analog digital. It's eventually moving from continuous time domain to discrete time domain. So that's the motivation. Motivation is to reduce sensitivity to process variations, and mainly in the components which don't have any correlation with each other, like GM of a circuit and capacitors and resistors. So they are independent. So now we want to move to discrete time domain, right? So therefore we don't have any value of the or any signal value which is continuously changing with time, because time is quantized. So therefore we need to have an element in the system which would be able to give us information at a given time stamp, and only at that time stamp, and again next time stamp. That means we need a kind of memory. A resistor is not an element, a simple passive resistor, for example. It's not an element with memory. It cannot remember past. Therefore, as soon as we want to discretize the time, so resistor becomes of no use, because it cannot remember what was the current in, say, 10 nanoseconds ago and then use it and then freeze it. It cannot hold it. So therefore, we need to look at something else which can have memory. So capacitor is a kind of memory. And that's why we can have capacitors in discrete time domain, but we cannot have resistors in discrete time domain. Of course, you may say that resistive memory. So that's a different thing, yeah. If we move towards resistive memory, yes. But right now, I'm not talking about that. It's just simply passive resistors that all of us know, and they are being used as one of the elements in active or passive filters. Because right now, we're talking about filters, though the notion of switch capacitor circuits is not limited to filters. It's actually, you can make a discrete time amplifier. It's all about moving from continuous time to discrete time. But any manner, even when we move to the continuous time to discrete time, and we are not talking about filters, say we are talking about amplifiers, still we need an element which can have memory. So we cannot use, say, resistors as a feedback to create a, say, inverting amplifier using op-amp, because that only works if we have continuous time domain. So now if we remove resistors, what can we do? Can we have an element which can emulate a resistor or operation of a resistor, but in discrete time? So we need to understand that what a resistor does. A resistor is an element, when we apply a voltage, it creates a current, and this current flows from one terminal to another terminal. So this current cannot be stored. So what can be stored? We can actually make an equivalent of this current over the quantized interval of the time. Quantized interval of the time in discrete time is defined by the clock period. Here is capital T. So capital T is quantized period. Therefore, we can only talk about nt when n is an integer number. And therefore, we have, say, t, 2t, 3t. Best case, we can also add some half of that, which is t by 2, and have some multiple in, integer multiple of t by 2. But we cannot go more than that. So therefore, still time is discretized. So therefore, what we can do is that we can generate an equivalence of the current in the domain where we can have a cumulative quantity which tells us an information about the amount of current which has flown through the resistor over a period of capital T. When we have information about that capital T, we can just put that cumulative information at the timestamp of nt, and then at the timestamp of, for example, n plus 1t, and then move forward. So in this way, we are discretizing. The same thing happens when we do sampling. When we sample a signal, so we have a signal of, say, x of t, continuous time signal. When we sample it, we eventually create a kind of cumulative information. Here, the cumulative information is very straightforward because it's just the value of the signal at a particular very, very narrow interval of tau, where we can follow the signal and then we stop. So therefore, and then we store that analog value in an analog memory, and then we'll wait for the next pulse to come. Okay, so now here, if we want to do that, we actually look at the element of the physical quantity which is related to the current, and it can be stored. Therefore, it's a quantity which eventually is a part of memory itself, and that is charge. We can always store the charge and hold it, assuming right now we are not considering the leakage in the capacitor, or leakage is negligible within the accuracy we are talking about. So therefore, if we look at the simple diagram over here, and then let's assume we have two clock phases, phi 1 and phi 2. So phi 1 is eventually the first half cycle of t, and phi 2 is the next half cycle of t. This is an ideal case. In non-ideal case, practical case, phi 1 is actually less than half of the cycle, And phi2 also is less than half of the cycle, so that these two clock phases don't overlap at all. Because if they overlap, this V1 will be shorted to ground, and there will be technical issues. Okay, so therefore they will work only in such a way that they don't overlap. And that's why the duration of phi1 and phi2, when they are high and the corresponding switch is closed, is less than T by 2. Okay, so now suppose this switch phi1 is open and phi2 say is open. Let's look at the initial condition. And then let's assume that some charge is stored on the capacitor, right? Some initial charge is stored on the capacitor. And then suppose the input signal, which is shown by V in of n, has a value like V1 at time equal to NT. So therefore, when we close the switch, the voltage on the capacitor will change to V1. From any value it was, it will change to V1. If we assume that the resistance of the switch is low enough to almost charge the capacitor within the acceptable error limit to the value of V1. So therefore, what we see on the capacitor C is actually change of charge with respect to the previous case, because charge is not necessarily zero at the beginning. So there is a change in the charge. This is delta Q over the capacitor. So this delta Q is dependent on the initial value, which is V in of 0 minus before closing the switch, and V in of n. Now, if we have a provision to discharge this capacitor always before every phase of phi1, then means initial value naturally becomes 0. And that is the reason this phase phi2 is included. So that to reset the memory and then store the new value. So this is, of course, one way of looking at that. There are the other ways when we don't reset the memory. So here in this case, memory is reset. So that means the initial value is 0. Therefore, delta Q is same as input multiply, of course, by C for a linear capacitor, because V in of 0 minus is 0. So this delta Q, which is the change in the charge, also corresponds to the equivalent continuous time domain circuit, where we have an R equivalent. And then we apply this input, V in of n, over one cycle of the quantized time. So every quantized interval is T, capital T seconds. So therefore, if we look at this time and then take the integral, we should get, because V in upon R is current, we should get integral of I dt. dt is missed here, so there is a dt over here. So that means that it will give us the value of the equivalent value of delta Q. So that's why these two are equivalent. And we want to see that what would be the equivalent R, which could have been kept over here between V1 and ground, effectively, instead of this entire circuit, and give us still the same integral of the current, which is the charge. So we just keep these two equal with each other, right? So V in of n is a constant value. So therefore, upon our equivalent will come out of the integral. Integral of 0 to capital T is just simply capital T. Now we have a concept of R equivalent, which is eventually 1 upon C, T upon C, right? Because here we have C and here we have coefficient T. And T upon C can be written also as C multiplied by sampling frequency. So interesting point here is, if you have an equivalent value of resistor with a value of T by C in continuous time domain over one period of T, same amount of charge is passed through the resistor as this case when we close the switch and then we accumulate the charge on the capacitor and store it. So we have defined this kind of equivalency. So what interesting point here is this resistor now is a function of capacitor, of course inversely proportional to the capacitor that we use. The advantage would be, now if we have RC, suppose I want to make a filter with a particular RC or a circuit with a particular RC, suppose C2. So R equivalent C2 becomes actually C2 upon C multiplied by T. Advantage here is instead of RC, now we have ratio of two parameters, which are in here value of capacitors, which are of the same type, and therefore they are absolutely correlated. For example, air temperature coefficient could be exactly same, very close to each other. So they can eventually be of the same type, and therefore the ratio of the elements now will have much less sensitivity to the process variations as compared to the RC. So this seems that fulfilling the target or the objective that we had to make it independent of process variations. So this is the same concept, which eventually explaining that what happens when phi2 we close the switch, so naturally charge get discharged and again is reset. Of course, here we connect it to ground, right? We can also connect it to a voltage. That is equivalent by saying that we have connected a resistor between the two voltages or between the two terminals. That means that we can have a single-ended resistor from input to ground. We can have a floating resistor or the resistor which is connected between two nodes and it's not grounded. One terminal is not grounded. But concept is same. The only difference is that here we don't have the reset. So here actually every time charge is set. In phase phi1, charge is set to CV1, which is the value of the input when we close the switch. And charge will be CV2 when we close the second switch, controlled by phase phi2. So therefore here delta Q eventually is CV1 to CV2. So delta Q usually is the Q for the new time minus the Q for the previous time stamp, because now we are talking about discrete time only. So for example, Q at time equal to N minus Q at time equal to N minus 1, or vice versa. For example, Q at time equal to N plus 1 minus time, Q at time equal to N. So this is delta Q, which is happening between two consecutive clock phases. But both of them resemble same thing, which is a resistor. But what happens when we do this emulation? What happens for equations that we use? Because equations also now move from continuous domain to discrete domain. How equations change? In continuous time, we just simply write V equal to Ri. If, for example, V is changing with time, I also will start changing with time the same way. Suppose if V is sine wave, I also will be sine wave for a constant resistor, linear resistor. But what will happen here for the equations? So to create this kind of equivalence of the two cases, we just look at the operations. Okay. Let's assume we look at the operation of an integral, right, in continuous time domain. So you know that, for example, in the capacitor, voltage is an integral of the current, right? So we integrate the current to generate the voltage. So let's see what is the equivalence in general before even being, biased with the electrical or electronic circuit applications. In general, what would be the correspondences between time domain, continuous time domain and discrete time domain? So this integration helps a lot. In fact, you know that this converting continuous time to discrete time is already used in numerical analysis. In fact, all circuits, not even circuit simulators, any kind of simulator, which is solving the equations in time domain, use the same concept. What they do is that they eventually discretize time. Therefore, they convert differential equations to difference equations. And that is the way they can solve equations in an intuitive manner and point by point. That's why actually all simulators do the discretization implicitly. And that's why if you zoom well on the output of a simulator, you will see at the end of the day, it has a time step, delta t. So it doesn't have continuous time. Continuous time even doesn't exist in a simulator, because that means resolution should be infinite, which is not possible. So it's the same thing. In fact, what we are doing here is what we are doing in that numerical analysis. So let's suppose we look at one interval, say from n-1 t to nt. And this is x of t, continuous time. So we are looking at one interval of this quantized time. Time is quantized, means that we are looking at n-1, then n plus 1. So in between, there is no information. It's quantized. So therefore, on the right side, we have continuous time domain. But the limits of the integral are two consecutive quantized value of time, n-1 and n. And suppose to make it very, very precise, we have to mention this point. If we start from n-1 minus, that means extremely close to n-1, but not n-1. For nt also becomes extremely close to nt, but not nt. If we start extremely close to n-1 t, but not n-1, for nt also becomes extremely close to nt, but not nt. We keep this in mind so that we will have always the exact duration of the integral as capital T. Okay. Another approximation we make is that this sampling interval, or this interval of the quantization, is low enough, which is not correct. Like, for example, in the example I have shown here, sampling frequency is actually low, is not very high, so that input is changing significantly within one cycle of the input clock. But suppose if you look at the second case, when the actually period is chosen relatively fine, so you can consider the input is almost constant. And this constant value is shown here with a red dotted line. Same thing is for this cycle, red dotted line. Now you can choose which one to choose. For example, here we choose the initial value on the left side of this interval as the constant value. That's why the staircase you see will appear in this way for every interval. So we consider this left side value as the constant value of the input. Same thing for the next discrete time interval. So therefore, this integral actually becomes, because we approximate by x at n-1 when we integrate from n-1 to n, so it becomes capital T multiplied by x n-1. So therefore now we have the eventually conversion of this integral to discrete time. This is exactly what simulator does. And what is this integral? So integral is y of t, right? Y of t is integral of x of t. This is the way we define y of t. Therefore, y of t at nt minus n-1 t, which is this integral, is t, my capital T multiplied by x n-1. So this is eventually difference equation associated with integrator. So integrator in this continuous time domain becomes a difference equation in discrete time domain. So in continuous time domain, integration becomes a difference equation in discrete time domain. That means now if we go with a conversion, we get one interesting relation. So you're familiar with Z transform in discrete time. So I don't talk about it, I just use it. So eventually what we do is that we have a difference equation. Y of n minus y of n-1. We can remove t also. This is implicitly understood. There is a t. So y of n minus y of n-1 is equal to t multiplied by x of n-1. So now this is an integrator, and the transfer function of an integrator in S domain, because S domain, Laplace domain, is the generic complex frequency domain for continuous time. Conversion of a mapping of x of t to x of s, and mapping of y of t to y of s. So that transfer function is 1 upon s. That is understood. That is well known. Now we have the equivalent of that transfer function in Z domain, because now we have derived it. In fact, we have approximated this integral with a difference equation. And that difference equation, if you just write the equation and then take the Z transform from both sides, so this side will be 1 minus Z inverse into Y of Z, and right side will be T X of Z inverse into X of Z. Now, if you multiply numerator, denominator by Z inverse, by Z, sorry, you will get this relation between Y of Z and X of Z. Means Y of Z upon X of Z becomes T upon Z minus 1. And if you are more comfortable with Z inverse, like I am more comfortable with Z inverse, you can write it with T Z inverse upon 1 minus Z inverse. So that means that the transfer function in continuous time, which is 1 upon S, can be approximated by T upon Z minus 1, provided we consider the initial value of the quantized time interval is the constant value. When we consider this is called forward Euler approximation. So we consider the first first point as eventually the constant value of the input. So that's why it is called forward, because from here we move forward to NT. So it's forward Euler approximation. Now what it says is that what are the correspondences between S and Z? Means that if you have a transfer function of h of S, you have a circuit in continuous time domain which is h of S. This S gets converted to something like Z minus 1 upon T. So you know that in ideal sampling using impulses, actually Z is e to the power st, or Z inverse is e to the power minus st. It's actual relation between Z and S with ideal impulse sampling. But here we don't have any impulse sampling. We have to just sample and hold, right? Eventually sample it and hold it. In fact, we cannot sample it also. We have to track it for some time and then hold it. That's why more often track and hold is used rather than sample and hold. We cannot sample at 0 second. That's why this still is not very practical. Practically, you track for some time and then you hold. It's because the switch here has to be closed for some non-zero time. That's why there is a duration when we track the input V1, input V in, which has value of V1 here. And then we open the switch. That means we track input and then we hold on capacitor C. So this is a very interesting relation. If you are comfortable looking at Z as a function of T, which is like I am more comfortable with this way, Z is ST plus 1. Now, if you remember that Z is equal to e to the power st, this is eventually the first term of that exponential relation. Means when we move from ideal impulse-based sampling to non-ideal sampling, and with full forward Euler approximation, we are using this idea of we are eventually using the first two term of that e to the power st. That means what we are considering is that the sampling that we have, that period of sampling t, is really very low as compared to the time, very high, sorry, what I'm saying, very low as compared to the time required for input to change. In other words, sampling frequency is much higher than the maximum frequency of the input. So that in one cycle of the sampling clock, input doesn't have enough chance to change. And this approximation becomes almost valid. So this is the first approximation, forward Euler approximation. And this is the way it takes us from S domain to Z domain. So to give you now an example of the practical circuit. So if I remove this phi1 and phi2 and capacitor, and then I replace it with a resistor, you will see that simple integrator, that RC integrator that you can make using an op-amp, right? Now let's remove that resistor and replace it with a switched capacitor. So we learned that we can do that and we can create an equivalent resistor. In fact, the circuit that I'm showing here, this is equivalent with the same circuit shown here. The only thing is, instead of the actual ground on the right, we have virtual ground, but it's same. So eventually we have a resistor, and this is the capacitor, which is integrator, and this is op-amp. Now see what happens with a continuous time RC integrator. If it is brought to the discrete time, what happens for transfer function? So because here we are in the discrete time, so we write discrete time equations. First in phase phi 1. So in the first phi 1, let's assume that this is n minus 1, right? We are talking about forward Euler approximation, n minus 1, right? So we are here. So charge which is stored is C1 Vn n minus 1, because switch is closed, Vh will be same as Vn. So therefore, it's a simple Q equal to CV equation. So we move to the phase phi 2. Now phase phi 2 becomes the phase of the next clock phase. So therefore, we change n minus 1 to n. So now in phase phi 2, now we have the discharge of this capacitor into this C2. And this is the way integrator works, right? Current flows from left to right and charges capacitor C2 when we have a resistor here. So here, instead of having continuous time current to charge resistor, we charge capacitor with pockets of charge for every cycle of the clock. So for every phi 2 phase, these pockets of charge are transferred to C2. So therefore, we have moved to discrete time. Therefore, we have to charge the C2 also with discrete packets of charge, rather than continuously charging. And therefore, because it's an accumulation integrator, so therefore, the previous value which has been on the capacitor needs to be considered. That means the initial value, which was V out n minus 1. And what we had here was V in n minus 1, right? So therefore, this delta Q is written over here. Charge that we had here was C1 V in n minus 1, right? So this entire charge now is transferred to capacitor C2. And because the charge is considered positive on the right side, so this transfer charge is appearing with a negative sign. And the initial value was the previous cycle value. Okay, so therefore this is the new charge, which is eventually previous charge added to the new charge. So it's a new charge now. Q of C2 at time equal to n, which is same as C2 V out n. It's a simple linear capacitor. Therefore, now if you look at this equation, we have eventually again a difference equation. V out n is V out n minus 1 minus C1 V in n minus 1 is, if it is because it's a integrator with a negative sign. So if you just take the Z inverse from both sides, you get this relation. So this relation is actually equivalent of the minus 1 upon RC, 1 upon S, right? That is equivalent of the integrator that we have in continuous time domain. But the interesting point is, in continuous time, we had minus 1 upon RC. And if R and C change, so the gain of the integrator changes. But here, gain of the integrator is C1 upon C2, which is very much immune to process variation. So ratios don't change too much due to process variations. Z inverse 1 upon 1 minus Z inverse is eventually approximation in forward Euler. This is what we derived here as well, right? Here, 1 upon S is 1 upon Z minus 1. If you multiply by Z inverse, becomes Z inverse upon 1 minus Z inverse, which is same thing that we have here, Z inverse upon 1 minus Z inverse. So this is the new integrator or equivalent integrator in discrete time domain. So therefore, what a switch capacitor circuit does, and it takes advantage of switching the capacitor in a periodic manner, charging and discharging it, so that we would be able to emulate operation of a resistor, but with discrete packets of charge. But we can implement whatever we have in the continuous time using discrete time. So how would be the eventually transfer function? So this is eventually the transfer function. See, this is Z inverse upon 1 minus Z inverse, right? So you can just replace. So you can just replace the equation for Z. So therefore, it can be approximated with minus C1 by C2 upon J omega t. See, why we use this omega t much less than 1? Because this is going back here. See, Z was ST plus 1, or S is Z minus 1 upon T. So as I told you, like these are the first two terms of e to the power ST. And then if we move to the J omega T, which is shown with capital omega, because we have the analog or continuous time domain and we have the discrete time domain. For continuous time domain, instead of a small omega, we use capital omega. And we use a small omega for the discrete time domain. That's why here capital omega is used. So if omega t is much less than 1, you can ignore other terms of the exponential. See, this is actually 1 upon z minus 1. So you can ignore all terms of z, which is e to the power st, except the first two, which is 1 plus st. And because 1 minus 1 will get cancelled, so st remains. And S is actually j omega, because now we are talking about only j omega domain, e to the power j omega t. Means that we are just talking about Fourier's frequency. So therefore, it can be approximated with this relation. And as you can see, this relation actually is an integrator. But the coefficient of this integrator now is minus C1 by C2, or gain of this integrator. Upon j omega t is indeed an integrator, right? 1 upon j omega is a transfer function of an integrator. And equivalent resistor is effectively T by C1, right? And C2 is the capacitance of the integrator. So now we have been able to make the first translation from continuous time domain to discrete time domain, and showing that an integral remains integrator remains integrator in discrete time, as long as we make sure that the sampling frequency is high enough to make the approximation right. Okay. So, and then, by the way, in this analysis, I consider this is the small signal analysis. Therefore, I made a positive terminal AC ground. If we operate with a single supply, so this will be a reference, common mode level. And input also will have that common mode level inherently. But right now, I'm talking about only small signal transfer function. So, you can also have similar transfer function, but with a technique which is called bottom plate switching. Because here you can see the bottom plate is grounded. It is not switching. You can add two switches, implement the same function, but it helps you later on, we'll see, to take care of the charge these switches inject on the capacitor. Because one of the practical issues with the switch capacitor circuits is the parasitic charge these switches inject to the capacitor when they turn off. For example, when phi2 turns off, not turns off actually, when phi1 turns off, at that time it will inject some charge to C1. And that charge cannot be discriminated from the charge which is stored to Vin. Therefore, it creates error. When phi2 is closed, that charge also will get transferred to C2, and therefore there will be error, which depends on the input. That's why there are techniques to reduce effect of that charge. I don't get into details, and that is called bottom plate sampling. So this circuit does the same thing the previous circuit does. It stores Vin on C1, it discharges C1 on C2. It does the same thing, but instead of making bottom plate completely grounded always, it actually allows both plates to get switched between ground, and this P eventually is switched between virtual ground and ground. This one is switched between ground and V. But that is good enough. That switching can be shown later. It provides an opportunity to discharge that extra charge, which is stored on capacitor C1. Even implicitly, I can qualitatively explain it here. when S1 is opened, so some parasitic charge is stored on C1. When you switch S2 to ground, this charge gets discharged to ground. That's the main reason it is possible to get rid of this problem. But it can be proven very nicely and it can be shown with details how this is done. So, but anyway, so bottom plate switching also is something that you might hear a lot. Actually, bottom plate switching is nothing special. It actually consumes more switches even. The only point is it makes the circuit to be immune of, or relatively less sensitive to the parasitic charge, because it avoids this parasitic charge to move to the next stage. But here it is not, because as soon as you open the switch, charge is here and is transferred to C2. But here, after S1 is open, then S2 is closed. Therefore, charge first gets discharged, and then S4 is closed, and then the charge stored on C1 is transferred to C2. So now if you go with different approximations that I don't explain further, because you can consider, say, instead of the first point to be the constant value of the x of n, or n minus 1, n. You can consider second value or final value. Then you will get, or you might get average of them. That's why you will get different approximations. This is the same thing that we have in, again, numerical analysis. When you want to convert an integral to the approximation, you have different ways, right? Trapezoid rule, forwardular, backwardular integration. It's exactly the same concept. That's why you can just derive for yourself. So in this case, for example, forwardular z became st plus 1, right? Or 1 plus st. If st is very small, actually it can be written as 1 upon 1 minus st. This is another approximation of exponential function when st is very small, magnitude of st. So that is backwardular approximation. If you use average for the constant value of approximation for the input, you will get bilinear approximation, which is more accurate than this too, because it uses average. Only implementation of bilinear needs more switches. So that is the price we pay. And the relation between z and s now becomes as a function of z minus 1 and z plus 1 both, or 1 plus ts by 2 and 1 minus ts by 2 both. So it's like, a kind of combination of the forward and backward Euler. That's the beauty. So now, as you can see, we have approximation of exponential function with this kind of linear approximation, or it's not linear, it's a line. So what would be the implication? Implication would be we will have some distortion when we move from the transfer function from continuous time to discrete time, because it's based on approximation. Higher sampling frequency will give us less distortion. Let's look at the forwardular approximation. So you know that if you go with the exact conversion, which is e to the power st, and replace s by j omega, if you are talking about only Fourier's frequency, j omega axis will be converted to the circle, which is unit circle, a circle with a radius 1 in z plane, because it is z is equal to e to the power j omega. And capital T also should be there, e to the power j omega t. So e to the power j omega t means magnitude is 1. So it shows points on this circle. But when we go with forwardular approximation, actually z becomes 1 plus j omega t. What is 1 plus j omega t is here, right? This line. This is 1 plus j omega t. When omega is 0, it is 1, which is this point, which exactly matches the conversion that we have from e to the power j omega. But for other values of omega, it gradually, as omega increases, it deviates from this circle, and that is the source of error. So this is small omega, that is, now you understand. We use small omega, even d means discrete time, so that to show this is the sigma and omega for the discrete time frequency, which is z. So it's not s. J capital omega is in the S plane. So this is the approximation. which is happening. If omega is 0, there is no approximation, it's perfect. Omega 0 is mapped to discrete omega 0. But other frequencies are not mapped exactly. And that is the reason we have error. And another point here is, these actually points are outside unit circle. Therefore, you know that if there is a transfer function, poles are outside unit circle, that transfer function is unstable. Or practically, it may show peaking in the actual use. So that is what exactly we need to understand. If we use forward Euler approximation, and we have some poles in the H of S transfer function in continuous time domain, they actually may be mapped to poles outside unit circle, and therefore discrete time circuit may even become unstable. So this is something that we have to be careful about. And therefore, it may happen that actually because of this, even if it is not unstable, poles become closer to unit circle circumference. Therefore, at least some peaking will happen, and specifically in the passband age. And as you can see, so it cannot generate any zero on the unit circle, because there is, other than this point, there is no other point. Other than omega equal to 0, there is no other point which matches this line, 1 plus j omega t. So therefore, yeah, it's only that omega equal to 0. Therefore, if you have, for example, some zeros in the transfer function, which are happening at some frequencies, j omega frequencies, for example, those zeros will disappear in discrete time transfer function. So eventually, we don't have any infinite loss in the stop band. So suppose, for example, you have some Chebyshev transfer function in S domain. When you move it to a Z domain, map it using forward Euler approximation, those zeros in the stop band disappear. So therefore, you may see actually the value of the output, or the eventually magnitude of transfer function in a stop band may slightly increase because of the removal of zeros. So similarly, if you go with backward Euler, which is the other way around, approximating a constant value with xn rather than xn minus 1, so you will get similar approximation, but interestingly, that becomes a circle rather than line, and actually it becomes inside unit circle. So this is image of the, or mapping of the j omega axis to the z plane, which happens. And that becomes a circle with a center at 1/2. You can derive it. It's easy to derive it. And then you will see this small circle. Eventually you derive it, you will see it will be a circle with a center of 1/2 and radius of 1/2. So here, actually, it's other way around. So if you have high Q poles in the continuous time, which may create peaking in the continuous time transfer function, they appear with lower Q in the discrete time, and therefore the peaking will reduce. And if you have very sharp passband edge, because now Q of the poles is reducing, so edges become more kind of, smooth, and the kind of what is called rounding effect. So it's not very sharp transition for the transition band. And of course, if you go with bilinear transformation, that we use the average of the two, x of n and x n minus 1, we actually get a mapping which is exactly on the unit circle. And that's why this is one of the best approximations. And the relation between the omega of the continuous time and omega of the discrete time is given by a tan function. And if this omega d is very small, omega of discrete time, which is equivalent by saying sampling frequency is very high, so then which is equivalent by saying sampling frequency is very high, yes, which means that the T, capital T, is very small, then tan omega d by 2 will be approximated by tan omega, will be approximated by omega d by 2. 2 and 2 will get cancelled, and capital omega becomes small omega, or discrete omega, divided by T, which is exactly what we would like to have. Just a linear relationship between the two omega values. Okay, so this is a kind of basic example, both in circuit domain as well as the transfer function domain, so that to understand the relation between the two domains. So if you have any question, you may ask.
Participants, any questions? Participants, you can write a question in chat box if you want. Or you can unmute your mic. No questions, ma'am.
Okay. Fine. So, do you want me to continue with one more lecture?
Yes, ma'am.
Yes. Okay, so let me just a little talk about the next one as well, next module. Yeah, so this is again continuation of the same topic, and this time I have also given, in addition to Ken Martin's book, David Jones Ken Martin book, also new Bezat Razavi's book, second edition 2017. It has a chapter, Introduction to Switch Capacitor Circuits. Yeah, so this is similar to the example I gave you. So it's just a repetition of the same. Replacing resistor with a switch capacitor equivalent and converting from S domain to Z domain. This already I have covered. This is the same thing. By the way, I can also tell you about the integrator of 1/1 minus Z inverse. This is actually good to see that how this is happening. If we don't have approximation, see, I gave you approximation in the previous case, so that we end up with minus C1 by C2 multiplied by 1/J omega, right? Let's assume that this omega t is not very small. See, this small omega or omega d is same as capital omega multiplied by t. So let's assume that the approximation is not in such a way that we can really consider only the first two terms. So let's write the actual values, right? So see what happens for the transfer function. So the transfer function, therefore, here will not be only the first. So we will write it exactly the way it is. So small omega is capital omega multiplied by t. And then what we do is that we just replace the values. And therefore, this becomes e to the power minus j omega. And then you know that e to the power minus j omega can be written as, you can just take the factor of e to the power minus j omega by 2. Take it out, which will get cancelled with this term. And therefore, you will have e to the power j omega t by 2, j omega by 2 minus e to the power minus j omega by 2, which becomes 2 times of j sine omega by 2. So that is exactly what we do here. And then we have it effectively this transfer function, right? So as you can see, if I get, this is the way also Ken Martin writes. If you just take this part out, because this is minus C1 by C2 gain of integrator, this is 1/J omega, which is the gain of, which is the transfer function of integrator. And e to the power minus j omega by 2 also is not a big issue. It's just a linear phase, which will give some delay. So therefore, these three are kept aside. Extra term that we have is here, omega by 2 upon sine omega by 2, right? So it is this function eventually adds distortion if we don't have enough high sampling frequency. If we have a very high sampling frequency, that means omega is very small, because omega is capital omega multiplied by t. If t is very small, omega t is approaching to 0. That means small omega approaches to 0. So sine omega by 2 is omega by 2, they cancel. And this is what we considered in the previous example. If we don't do, then means that this is if you reduce sampling frequency, you see more and more distortion. So this is a very good example to actually see the effect of distortion. And then see, and another interesting point, that's why I ask the students also, really you plot and see what happens for the transfer function of the integrator if you have this distortion. How does it get affected? See, because actually you can cancel this to omega, and your integrator, instead of to be 1 upon j omega, is 1 upon sine omega by 2. Sine of omega by 2. At low values of omega, it is giving you 1 upon omega. But at higher value of omega, it's eventually getting saturated, right? Because sine for any value finally gets saturated to 1. It cannot go beyond that. So it gets saturated, and that is the reason you see the distortion. It eventually makes the omega, which should be supposed to be omega, to get converted to sine omega by 2. It eventually makes a compact version of this. And therefore, your plot becomes actually 1 upon sine omega. Of course, this is for the omega when omega is not 0. This is not for omega equal to 0, because for omega equal to 0, then already we have the equivalence. So this is for non-zero omega. It will give you eventually for omega, which is more than the eventually low frequency that we have, is an integrator. Other than that, you see the exact distortion. And this is very interesting to actually plot it. And MATLAB or any kind of simulator, Scilab and equivalent can give you the plot as you reduce the sampling frequency. For a given signal bandwidth, for example, you consider 1 megahertz signal and then reduce the sampling frequency and see the effect. So this is the bottom plate switching that already I talked about it with you. And here is another example when actually we have a kind of, second order, first order, because one of them creating 0 only, and capacitors are forming a loop. That's why, in fact, this capacitor actually capacitors are not forming a loop. This capacitor is only adding 0. It's not adding any pole because it is connected between input and virtual ground. But it is just to increase the eventually complexity of the transfer function. We had 1 resistor, 1 capacitor. That already I showed you. Now we add 1 more capacitor at the input path, which adds a 0, and 1 resistor here, which makes it a lossy integrator. And then again, we have this transfer function. So you can again replace and go with, say, different approximations. So here I have used backward Euler approximation and get h of z. And then this also will have its own pole and zeros in z domain. So this is just a conversion as an example. And this is the implementation using the backward Euler approximation. And here is eventually really getting into the details of the transfer function. This is given in Ken Martin's book up to some limit. And it shows you really how you can get into the details of the transfer function if you don't use any approximation. And when you use approximation, when you consider really sampling frequency is high or capital T is very low, so all this sine and cosine can be approximated to the omega or 1, and therefore you will get the actual transfer function. This is what I have written here. Sine can become almost same as argument, and cosine becomes 1, then you will get the actual transfer function. If this is not valid, then you will have distortion. So your transfer function is interesting. Instead of being a function of omega, it's become a function of cosine and sine of omega in discrete time. And and then I have given a numerical example. For example, let's assume we want to make a first order low pass filter. Sampling frequency, say 1 megasample per second, minus 3 dB cutoff frequency, say 20 kilohertz, like audio frequency. And then we want to have a zero gain at Z0, which is equivalent with high continuous time frequency. That means actual continuous time has just a zero, has a pole, and no final zero. And finally, DC gain is 10. So this is just to get an idea how to design it. Okay, so at S equal to infinity, gain is 0. So that means that there is no 0. And therefore, one of the capacitors practically becomes 0 because we don't have it. It is equivalent by this. Here, if I have C1, I have a 0 in the transfer function. If C1 is 0, the 0 actually will happen at S equal to infinity. So therefore, this is, I just simplified it, and therefore it reduces only to realization of one single pole. So this is location of pole and zeros. For 0, of course, C1 is 0, so 0 is not in the picture. And we have the pole. And this is the actual transfer function if this approximation is valid. And because C1 is 0, so therefore, after keeping C1 equal to 0, we get this new transfer function and then convert it to j omega because we are interested in Fourier's frequency only. So this is the actual transfer function in Z domain in j omega d, of course, on domain. Fourier frequencies of discrete time. So it's the final transfer function. And then say cutoff frequency is say 20 kilohertz. So therefore, this is the cutoff frequency, right? So therefore, this we will keep at 20 kilohertz. And of course, we have to write it as a function of sampling frequency because this is omega domain. Omega changes between 0 and 2 pi. So it gets converted to 2 pi by 50 as a function of Fs. And we will get the ratio of capacitors. This again is also given, which is eventually ratio of Ca and Cb, which is 10. Because that happens when S equal to 0 or Z is equal to 1. So these two will get cancelled. It is Ca upon Cb. So now you have ratio of capacitors. So you can choose one of these capacitors and the other two will be derived. In designing discrete time always is like that. You always get ratio of capacitors because everything is determined by ratio of capacitors. And that's the beauty of this domain. Makes things very precise and controllable. Post-fabrication, there is no issue. Okay, so this is more about numerical example. A similar example is given in Ken Martin's book, but I try to expand it and explain it with some more details. And this is, of course, implementation backward. See, it's very interesting. For example, in forward Euler, we first charging the capacitor and then discharging it, right? Do you remember? Here, what happens is that in one phase you charge and transfer to the next capacitor. And in the other phase, first you discharge. That's the difference between the implementation of the forward Euler and backward Euler. Going back here. Sorry.
Ma'am, sorry for interrupting. There's a question in chat box actually. So should I read it for you?
I think, yeah, can I see? Yes, I can see. What is the physical significance of Z in the transfer function as mapped to the electronic circuit switch capacitor? Actually, Z is same as S. In fact, Z is a way of looking at S. Because writing e to the power st is not very convenient. That's fine. Just it's like a change of variable. It's nothing more than that. Therefore, all it says is that how you are mapping the frequency. In fact, its frequency is same. Is S actually is S, but but it becomes a function of S. Means that you don't deal with exactly S unless if you have a very high transfer function, a very high sampling frequency, like the approximations we have here. See, Z and S are same. It's just like Z is a function of S. Z is not a new domain. Z is not a new domain. Z is same as S domain. But it's only a mapping from S to Z. So therefore, it's not like that we have new frequencies and we have two different set of frequencies. No, still we have the same S. If we know the, say, j omega frequencies, then we know j omega frequencies in discrete time. It's not like that they are independent. They are dependent. They are same. But this is an approximation which is happening because we are not actually getting the signal in continuous time. We are using the samples of the signal in discrete time. Therefore, we are losing information. Since we lose the information, therefore, naturally, we expect also to lose information in frequency domain. Now, loss of information in frequency domain is given by this approximation. It says that it's not like S, right? Z is not equal to S. Okay, let's put it that way. Z is not equal to S. And why it is not equal to S? Because, and they say equal 1 minus ST is because we are using the approximation.
I think some noise is there. I will mute it.
Okay. Yeah, so is that clear? I don't know if I answered the question. So, okay. So both are frequency domain, both are conveying same information, but the relation is not an absolute linear relation because of the distortion that we have. In this mapping, from continuous time to discrete time, or moving from continuous time to discrete time, we lose the information. And that naturally affects the relation between S and Z. In fact, if the sampling frequency is very high, here we showed, right? No, it was in the other example, but that's okay. When eventually omega d and capital omega are linear function of each other. In fact, omega d becomes capital omega multiplied by t, a perfect linear relation, only with a scale of capital T. So that is the right mapping, but that will not happen. And that's why it tells us it's not a new frequency domain, it's the same frequency domain with distortion. So that's why Z is same as S. In general, historically, Z was called Z because it was more convenient to use Z rather than e to the power STS. It's ST, e to the power ST. It was very difficult. See, if you want to use e to the power j omega d, it's more difficult, right? Because you have an e. Historically, Z was used. That is the reason why we are not using directly. Otherwise, we are still in the same frequency domain. And if you have enough sampling frequency, high sampling frequency, e to the power j omega d gets converted to 1 plus say j omega d, or 1 upon 1 minus j omega d, which at least gives us the first order relation. These are very important, in fact, these are important concepts, and it takes some time for you to digest it. It is true. But if you work on it and try to completely understand these fundamentals, the rest of the things is straightforward. So I believe always, what is important in learning is not to have a bulk of, what we can call it, bulk of information. We need to know some fundamentals well. If we know fundamentals well, the rest can come along. I remember I had a faculty during my PhD he always was mentioning this statement, but then I didn't believe in that at that time. But then I noticed he was absolutely right. He was telling that you can always learn what you want to learn. That's not a problem. If your fundamentals are correct and you have learned the fundamentals well, rest of the thing you want to learn, you can learn on your own. I think and later on I recognized he was right. What is important is to make sure fundamentals are understood. Rest will be understood well. But if suppose we don't know how to write, for example, a simple example, how to write, words, so we cannot write sentences. But if we know how to write words, we can write sentences. Of course, we may need to still work out, but definitely it is not as difficult as learning at the beginning how to write words. Here, fundamentals are the key. So, and the rest of the things are formulated because they are systematic. Many design aspects, specifically in filters, are systematic and automated. But fundamentals matter. To decide about the sampling frequency, see how much we have to increase the sampling frequency. Even, there are techniques which is called time warping. For example, it's like, pre-distortion technique which is used in power amplifiers. When we know that we have a mapping or a transfer function that in discrete time which creates distortion, so we actually create the inverse of that distortion in the continuous time, so that after the distortion we get in discrete time, so we get actually close to what we want. So these techniques are also available, because we may not have always luxury of increasing the sampling frequency to a very high value. See, this is the very key constraint, omega t much less than 1. The concept is omega upon eventually t is eventually 1 upon fs. Eventually making the maximum frequency of signal to be much less than the sampling frequency. That's the meaning of that. Means the signal bandwidth should be much less than the sampling frequency. That means we have to be well above Nyquist rate. Then we will get really, do Nyquist say, if you go with Nyquist rate, you will get information back. But that happens only if you have ideal sampling with impulse, which is not practical. So therefore, we have to be well above Nyquist rate to be able to retrieve the information. So this is very important. And this is the meaning of omega t much less than 1. If omega t is much less than 1, S and Z are related only by a coefficient of capital T. That's it. And therefore, we don't see any distortion.
Ma'am, there's one more question.
Yes.
What are the application of switched capacitor circuits?
Yeah, so one of the application is eventually, suppose if you design a data converter, because data converters have sampling already available. So when you want to do the any kind of processing that you need before data converter, you can do it in discrete time. So that helps a lot. And some of the applications of discrete time happens within the data converters. For example, suppose if you want to have a discrete time delta sigma. So you will use eventually everything in discrete time domain. So main application of the discrete time circuits are in the application when you want really get rid of process variations. So you try to implement everything in discrete time domain. That's the main reason. That's the main reason. Plus, if already you have access to the sampling and you need to have the sampling, so you can push some of the processing into the discrete time. For example, I give you an example of this, why it is required inside the data converter. See, one of the techniques these days for improving resolution of converters is to do some kind of mismatch and noise shaping within the converter. Suppose if you have a, say, SAR ADC, okay? If you have a SAR ADC, you can actually do mismatch and noise shaping within SAR ADC, specifically for lower bits, which are close to LSB. So now to do that, you eventually, because you have already in discrete time when you are working with SAR ADC. So it's a clock-based conversion. So you have already got into the discrete time operation. So what it does is that divides new techniques. They divide actually the conversion into two parts, coarse bits and fine bits. And then for fine bits, because you are talking about bits and it's cycle by cycle, so it's a discrete time. So what they do is that they put a discrete time noise shaper, which is actually a kind of filter, because it's already discrete time. So they add that and then implement the transfer function they want in discrete time. So they get a process, almost process independent noise and mismatch shaping within the SAR ADC. This is one of the, in fact, latest examples. And that's why recently SAR ADCs are competing with delta sigma with respect to the resolution, because they can beat the energy consumption, but they cannot beat the area. This is one thing that yesterday also I showed you in Lakshmisha's work. We use delta sigma because it gives you compact solutions. In other PhD work, we are using SAR ADC, where we want to see how much we can improve the resolution and reach to low energy, even though we know that area is more. And there actually we are using discrete time noise shaping and mismatch shaping using a discrete time cycle.
Is any other questions from participant sides? The participants can unmute the mic if you want to ask any question. No question, ma'am.
Okay. Okay, fine. I hope you have enjoyed this discussion. I really like to talk to you and then just I really like this kind of topics, and to me appears that they are very interesting. I hope you have also enjoyed, and stop the presentation.
Okay. So I really want to thank you, ma'am, for
Most
accepting our
welcome.
request and giving a wonderful session on switch capacitor circuits filled with mathematical analysis of it. As all our participants are in teaching profession, so I'm sure they will be benefited from this talk and get an add-on from this session. So thank you very much, ma'am.
You're most welcome. Thanks. You have also done a good job of coordinating everything. Yeah.
Yeah. Thank you, ma'am.
Yeah.
Actually, it's my department, ma'am, electronics. So I am also part of it.
Okay. Good. Very good. You are all kind of active faculty members. Best of luck and all the best for all of you.
Thank you very much, ma'am.
Yeah. Welcome. Okay. Bye. Bye, everybody.
Bye, ma'am.
Bye. Thank you all. Bye.
Yeah.